Hello, good evening, and welcome to this session. This is our second session. In the first session, we have solved some problems related to basic review of thermodynamics. And in today's session, we will solve some problems related to steam power cycle, Rankine cycle to be more specific. Okay, so we will begin with question number 1. Question number 1 says, what are the components of a steam power plant? Okay, so very basic question. What are the components of a steam power plant? Okay, so a steam power plant has 4 components. One is pump, then boiler, then turbine and condenser. Okay, so what happens? Water steam power plant basically works on the working fluid is water. Okay, so water goes into boiler. In boiler, we provide some heat from combustion or some any other source. In the boiler, water becomes from liquid to gas. Okay, so at the exit of boiler, we get high pressure and high temperature steam. Okay, this high pressure and high pressure steam then passes through a turbine. Okay, in turbine, there is expansion process and we get some work output. Okay, and in boiler, we were providing some heat. Okay, so in boiler, there is some heat input. Okay, so after turbine, the at the turbine exit, we get low pressure, low pressure steam. Then this low pressure steam passes through a condenser where it condenses into a liquid water. Okay. Okay. Then this water goes into pump where its pressure is raised up to the working pressure of boiler. Okay. Here it will pass through a pump and pump will pressurize the water and it will send it to the boiler. So these are the main components of the steam power plant. Okay. Boiler, turbine, condenser, and pump. So part C should be the correct option. Okay. So steam power plant works on a cyclic process. There are 4 cycles. In boiler, there is constant pressure heat addition. In turbine, there is isentropic expansion if the process is reversible. If there are some irreversibility, then the process will not be, isentropic. In condenser, it is again constant pressure heat rejection, and pump, it is isentropic, you know, compression, you can say. Okay. So these are the main processes which are involved in a steam power plant. Okay. Question number 2. Steam power plants work on which of the following cycles? Carnot cycle, Rankine cycle, Otto cycle, or Bell-Coleman cycle? I hope this should be very easy to answer, that the answer should be Rankine cycle. Okay. Carnot cycle is the ideal cycle, but its implementation is very, very difficult. Okay. So Rankine cycle, obviously in Rankine cycle, we will not get the same efficiency as we were expecting in a Carnot cycle, but Rankine cycle is more practical. Okay, so Rankine cycle is used in steam power plants, not the Carnot cycle. Okay, because implementation of Carnot cycle is very, very difficult. Okay, just to give an idea, if we use the Carnot cycle, then in Carnot cycle there are two isentropic process and two isothermal process. So here you can see process 3 to 4 or turbine, you can see it is in the dome region. Okay, so there is mixture of steam and water. So turbine, for turbine it is very difficult to work for a low quality steam. Okay, so if there are some water particles, then it can damage the turbine very badly. Okay, and from 1 to 2 again you can see there are some, in the, it is in the dome region. So for pump again, it will have to handle the mixture. Okay, so pump and turbine both are designed to work for single phase. Turbines works very well for the steam, and pumps work well for liquids. Okay, and controlling this process, like if you want to stop the process, this expansion process in turbine at point 4, then it is very, very difficult to control this thing very precisely. Okay, so the precise control is very difficult, and turbine and pump have to handle two phase fluids, so it is very difficult to have a Carnot cycle. Okay, so the Rankine cycle is more practical one, so that is used in steam power plants. Okay, question number 2. So question number 3. Rankine cycle has a lower efficiency compared to corresponding Carnot cycle with the same maximum and minimum temperature. So what should be the correct option? We have to tell whether it is true or false. We have discussed just now in the previous question that Carnot cycle has the maximum, efficiency as compared to the Rankine cycle. Why? Because Carnot cycle, let us say this is our Carnot cycle, the red one. 1, 2, 3, 4. This is TS gram. In the previous question also, this was TS diagram. Okay. And if you make the Rankine cycle, which is working in the same temperature limits, then it will look something like okay, will look something like this. Okay, this green one is the Rankine cycle, and the red one is Carnot cycle. So maximum temperature for these both cycles is this T max, and minimum temperature is, let us say, this is T min. Okay, so both of these cycles are working in the same range of maximum and minimum temperature, but you can see that in Rankine cycle, average temperature of heat addition is less as compared to average temperature of heat addition in Carnot cycle, because in Carnot cycle all the heat is added at the T max, but in Rankine cycle uh, heat is added from this, let us say this is from this point to this point. There is whole temperature range of heat addition. Okay, so the average temperature of heat addition is reduced. Okay, so for this reason the efficiency of Carnot efficiency of Rankine cycle will be less as compared to efficiency of corresponding Carnot cycle. Okay, so this is the underlying concept. Okay, so if you want to modify the Rankine cycle so that you can increase the efficiency, what will you do? You will modify the cycle in such a way that the average temperature of heat addition is increased and average temperature of heat rejection is reduced. Okay, so whenever we modify any cycle to increase the efficiency, this is the underlying concept. Okay, and this is the reason that Rankine cycle has lower efficiency as compared to Carnot cycle. Okay, so this is true. Okay, so I hope this is clear. Just you can just note, to increase the efficiency, we should increase the average temperature of heat addition and reduce the average temperature of heat rejection. Okay, so in Rankine cycle, average temperature of heat addition is less as compared to average temperature of heat addition in Carnot cycle. So for this reason, the efficiency is lowered. Okay, so if this is clear, then we will move to the next question. Question number 4. Question number 4 says, the major heat loss in a steam power plant occur in. There are 4 options: economizer, boiler, condenser, or pump. So we have already discussed the processes. Two to three is boiler. Okay, 2 to 3 is boiler. In boiler, heat is added. Okay, heat is added. So this is heat addition process. Then 3 to 4, it is expansion. And if it is isentropic, then there is no heat exchange. Okay, isentropic in case of ideal cycle. So no heat exchange. So no question of heat loss. No heat exchange. Then 4 to 1, in condenser, heat is rejected. Okay, condenser. This is heat rejection process. And 1 to 2, again, it is pump. So in the ideal case, it will be isentropic process. So again, no heat exchange. Okay. So 2 to 3, heat is added. So no question of heat loss. Heat can be lost, but in net sense, it is heat addition process. Okay. 3 to 4, no heat exchange. So no question of heat loss. 4 to 1, Yes, in 4 to 1 in condenser there is heat rejection. Okay, and 1 to 2 again there is no heat exchange. So in condenser there is maximum heat loss. Okay, or heat rejection. So condenser should be the correct option. Okay, so we will move to the next question. Question number 5. Question number 5 says the principal function of a cooling tower is to remove heat from water that goes into condenser. Okay, so you should be able to answer this question. This is false. Okay, this is not the you know working function of cooling water, sorry, cooling tower to remove heat from water that goes into condenser. Okay. Question number 6. In a thermal power plant, a condenser is installed to condense the exhaust steam coming out of where? If you just check the previous diagrams, there was turbine, then there was a condenser, then there was a pump, and there was a boiler. So this was the cycle. Okay. So condenser is installed to condense the exhaust steam coming out of where? From the turbine, right? So the turbine should be the correct option. Okay. So very easy. So I hope that all the devices and all the processes are clear. Okay. In question 4, there was one more device, economizer. So economizer basically is a heat exchanger. So what it actually do? There are flue gases, exhaust flue gases, which are coming out of pure combustor, where combustor is used uh, to heat the water in the boiler. Okay, so in the boiler there is heat addition process, and how the heat is added? From a combustion device. Okay, so from after combustion there will be some exhaust gases coming out. So these exhaust gases are quite hot, and this heat of these combustion gases can be used to raise the temperature that will go into boiler. Okay, so economizer basically is a heat exchanger. Okay, so if any new terms come, then we will discuss that as well. So question 6, I hope it is clear. Question number 7, this is a numerical one. It says that a steam power station has overall efficiency of 25%, 25%, and 0.5 kilogram of coal is burnt per kilowatt hour of electrical energy generated. Fine. We have to find the calorific value of fuel, and we have to take heat equivalent of 1 kilowatt hour as 860 kilocalorie. Okay. 1 kilowatt hour is basically a unit of energy that is equal to the energy that will be consumed in 1 hour by a device whose power rating is 1 kilowatt. Okay. And it is given the question itself that it is equal to 860 kilocalorie. Anyway, so steam power plant has an overall efficiency of 25%. So what is the efficiency of a steam power plant? It is the it is the power produced divided by the heat input. So what is the power produced? Power produced is power produced by turbine minus power consumed by pump. Okay. So power produced by turbine minus power consumed by pump divided by your heat input. Okay, so this is the efficiency of power plant. This is given to be 25%. Okay, and it is given that 0.5 kilogram coal is burned. Okay, so let us assume that all the energy that is produced in combustion, all of that energy is utilized. Okay, let us assume 100% efficiency of boiler. Okay, so whatever heat is released during combustion, all of that is utilized by boiler. Okay, so if the calorific value of coal is, let us assume it is C. Okay, C, let us say it is calorific value of coal. So 0.5 kilogram of coal will be equivalent to 0.5 multiplied by C, this much of energy. Okay, kilocalorie. Okay, so this is our heat input. Okay, this is our heat input. Okay, and it is saying that 0.5 kilogram of coal is burned per kilowatt hour. Okay, so 1 kilowatt hour of 1 kilowatt hour is the electricity generated. Okay, so that will be equal to network output. Okay, okay, so 1 kilowatt hour divided by 0.5 C kilocalorie is equal to 25%. Okay, so from this equation we can find what is C. Okay, so C will be equal to 1 kilo, just put the value of 1 kilowatt hour, it is 860 kilocalorie. Okay, so 860 kilocalorie divided by 0.5 kilocalorie into 100 by 25. So this will be your calorific value of coal or whatever fuel you are using. Okay, so we can calculate this value. Eight sixty multiplied by 100 divided by 0.5 into 25. So it is coming out to be 6880. Okay, so part B should be the correct option. Okay, so the calorific value is of fuel is 6880 kilocalorie per kg. Okay, so I hope this is clear, and we can move to the next question. Question number 8. Question number 8, it says that in a Rankine cycle, heat input is provided to, very easy question, heat is provided to the boiler. Okay, heat is provided to the boiler, and work output we are getting from turbine. Okay, and heat is rejected in condenser, and there is a pump in between. So pump is work consuming device. Work in is the pump. Okay. So the boiler is the device where heat is added. So we can move to the next question. Question number 9. Question number 9 says that the thermodynamic difference between a Rankine cycle working with a saturated steam and the Carnot cycle is that, okay, option A, heat is supplied to the water at temperature below the maximum temperature of cycle. Okay. Part B says the Rankine cycle is hypothetical. Rankine cycle receives heat at two places. Carnot cycle cannot work with the saturated steam. Okay, let us see all these options one by one. Option A says that heat is supplied to the water at temperature below the maximum temperature of cycle. This we have already discussed. Okay, there was a Carnot cycle, and if we make Rankine cycle working in the same temperature limits, then we get something like this. Okay. So heat is supplied to the water at temperature below the maximum temperature. Yes. So this T3 or T max, this is the maximum temperature, and heat is added in the process 2 to 3. Okay. This process 2 to 3, this is your heat addition process. And during this, all this process, during whole heat addition process, temperature is less than T max. Okay. So option A is correct. Option B says that Rankine cycle is hypothetical. No, Rankine cycle is not hypothetical. Okay. Ideal Rankine cycle, yes, it is impossible to achieve in the real life, but it is not hypothetical. Okay. Rankine cycle, the actual Rankine cycle is used in the steam power plants. Of course, there are some irreversibilities, so there is no ideal Rankine cycle. Okay. So it is not hypothetical. Option C says that Rankine cycle receive heat at two places. No, only one place, from 2 to 3 in the boiler. Last part says that Carnot cycle cannot work with the saturated steam. Carnot cycle can work with the saturated steam. Okay, actually, if it is working in the saturation region, then it will be easy to perform the isothermal process. Okay, because if you maintain the constant pressure, then in the saturation region, the temperature will be automatically constant if the saturation pressure is constant. Okay, so but Carnot cycle, it is very difficult, uh, to make the devices which can handle this two-phase flows. Okay, and some other, other applicability challenges. Okay, so option A should be the correct option. Okay, so we can move to the next question. Question 10. It says that Rankine cycle comprises of, this is a very easy question we have been discussing. We have discussed this thing many times. So there are four processes. In the pump, we assume that there is isentropic pressure rise. Okay. Then the boiler, we assume that it is constant pressure heat addition. And in turbine, we assume that it is isentropic expansion. And 4 to 1, we assume that it is isothermal heat rejection. And since temperature is constant from 1 to 4 or 4 to 1, so the pressure will also be constant because it is in the saturation region. Of course, we are talking about ideal Rankine cycle. Okay. So there are two isentropic processes. What are those processes? Expansion in turbine and pump. Okay, pressure rise. And two constant pressure or isobaric processes. What are those processes? Heat addition in the boiler and heat rejection in condenser. Okay, so heat rejection is a isothermal process, but since we are in the saturation region, so pressure will also be constant because temperature is constant. Okay, so there are two isentropic process and two constant pressure process. Okay, so the part B should be the correct option. Okay, so I hope this is clear, and we can move to the next question. Question 11. It says, which of the following is not a major component of a steam power cycle? We have discussed the components of a steam power cycle. There are four components: boiler, pump, heat exchange, boiler, condenser, pump, and condenser. Sorry, turbine. Okay. So which of these is not a major component? Turbine is a component, boiler is a component, pump is a component, compressor is not a component. Okay. Compressor is used in gas power cycles, not in the steam power cycles. Okay. So part D should be the correct option. Okay. Compressor is used in gas power cycles. Okay, compressor and pump, both of these devices increase the pressure, but pump work well for liquids, and compressor, this is designed to work for gases. Okay, so in a steam power plant, compressor is not used, pump is used. Okay, so this should be clear, and we should move to the next question. Question 12. Question 12 says that the actual cycle efficiency is calculated because of the thermodynamic irreversibility of the process. Okay, there are two cycles. One is ideal cycle, in which there is no irreversibility, and there is actual cycle, in which there are irreversibilities. So actual cycle efficiency is always less than ideal cycle efficiency, and the reason is there are irreversibilities. Okay, so we have to tell whether this statement that actual cycle efficiency is calculated because of thermodynamic irreversibility in the process. So this statement is true. Okay, the actual cycle efficiency, or the actual, it is less than ideal cycle efficiency due to irreversibilities. Okay, so I hope this question is clear. We'll move to the question number 13. Question number 13 says the processes associated with the ideal Rankine cycle. This we have already discussed. Option A says two adiabatic processes, two isentropic processes. No, there are two constant pressure processes as well. Option B says that constant volume process and two isentropic process. No, there are two isentropic process, but there are two constant pressure process. Question C says that two constant temperature process and two isentropic process. No, this is also not correct. Last part says that two constant pressure process and two isentropic process. Yes, this is correct. Again, I will repeat that constant pressure processes are in the boiler, heat addition, and condenser, heat rejection. And isentropic processes are in the turbine, expansion, and the pump. Okay. So it was easy question. So we will move to the question number 14. Question number 14 says the ratio of pump work input to the work developed by the turbine work. So this is just a definition based question. The ratio of pump work input to the work developed by turbine. It is called what? Back work ratio or isentropic efficiency or net work or thermal efficiency. Okay, we will discuss all these terms one by one. Let us begin with isentropic efficiency. Isentropic efficiency is defined as actual efficiency of a device divided by ideal process efficiency. So this is isentropic efficiency. Okay, of any process. Okay, net work, it is work output from turbine minus work consumed by pump. Okay, and thermal efficiency. Thermal efficiency is net work output divided by total heat input. And this back work ratio, this is work input to the pump divided by work output of turbine. Okay. Okay. So we want to reduce the back work ratio. Okay. If the back work ratio is more, then our efficiency will be reduced. If the back work ratio is smaller, then efficiency will be more. Okay. So this is how it is defined. So all these terms should be clear. So we will move to the question number 15. Question number 15 says, in a Rankine cycle, heat rejection obtained from, again, pump, what pump do? Pump increases the pressure. Okay. Pump increases the pressure. How much it increases? At least up to working pressure of boiler. Okay. Condenser. In condenser, heat rejection takes place. In turbine, expansion takes place. And in the boiler, heat addition takes place. So heat is rejected in condenser. So part B should be the correct option. Okay. So we'll move to the question number 16. Question number 16 says, in an ideal Rankine cycle, compression in pump is isentropic. So isentropic mean no entropy generation. So that means it is ideal process. So in an ideal Rankine cycle, there should be no irreversibilities involved. Okay. So pump, the process in the pump or compression in the pump, that should also be then isentropic process. Okay. So it is true. Okay. But in real cycle, there will be some irreversibilities. Okay. Question 17. Question number 17 says, which of the following is not a primary goal of subsystems associated with vapor power plants? Okay. So what is not a primary goal of vapor power plant? What is the primary goal of vapor power plant? Primary goal is that we convert the heat into work. Okay. How we are converting? First, we are making steam out of water. Then we are using that high pressure, high temperature steam to run a turbine, and we are getting some mechanical work. Okay. So this is the main objective, the primary goal of a vapor power cycle, to convert heat into work. Okay. Some part of heat into work. Obviously, there is some heat rejection. So option A says convert electrical power to the shaft work. No, it is not the primary goal. Okay. Part B says provide condenser cooling water. No. Part C says convert shaft water to electrical power. And last part says supply energy to vaporize the power plant working fluid. So what should be the correct option? Which is not the primary goal of this vapor power cycle. There are four, devices, and there are some subsystems. So which of these is not a which is not the primary one? Okay, let us see all these options one by one. Question A says convert electrical power to shaft power. We will come to this option later. Part B says provide condenser cooling water. Okay, so in condenser, if you are not providing cooling water, then condensation or the heat rejection will not take place. Okay, so this is an essential part. Okay, so this is an primary, subsystem. Part C says convert shaft power to electrical power. So shaft power to electrical power, if you are not converting, then how you will, transport your power produced? Okay. So in turbine, whatever shaft work you are producing, so with that shaft, there will be connected a generator, and that generator will produce some electricity, and that electricity will be supplied to the grid. Okay. So this is also a essential part. It is a primary part. Okay. Last part is supply energy to vaporize the power plant working fluid. So if you are not providing energy and you are not vaporizing the working fluid, then how will you get steam? If you are not getting steam, then how the turbine will work? So this is also a essential part. Okay. But part A, which says convert electrical power to soft power. So this is not the primary goal. Okay. This is not the primary goal, because you can supply the electricity to anywhere, and there it can be used to uh, run any device. Okay, there it can be used to there it can be converted into soft power. You can run a fan, you can run a cooler, or you whatever you want to run, you can run using electrical power. Okay, so part A, convert electrical power to soft power. This is not a primary goal. Okay. So question 17, I hope it is clear. We will move to question number 18. Question number 18 says, or a vapor power cycle with a turbine that produces 5 megawatt and pump that requires 100 kilowatt. The back work ratio is 2%. So back work ratio we have already discussed. It is defined as work input to the pump divided by work output from turbine. Okay, turbine is producing 5 megawatt. Sorry. Pump requires 100 kilowatt and turbine is producing 5 megawatt. So what is the back work ratio? So if you just convert this megawatt into kilowatt, then you will get 5,000. Okay. So this is 1 by 50. And if you convert this thing to percentage, you will get 2%. So in the question also it is 2%. The back work ratio is 2%. So it is true. Okay. Okay. So we'll move to question number 19. Question number 19 says, with a higher back work ratio, the actual cycle efficiency will be less. So we have already discussed this question, that if back work ratio is higher, that means a lot of power is being consumed by pump. So efficiency will be reduced. Why? Because net work output will be reduced. Okay. And if the back work ratio is smaller, then pump work input will be smaller and net work will be more. So efficiency will be higher. So in this question, higher back work ratio and actual efficiency will be less. So it is correct. Okay, true. Okay. We'll move to question number 20. Question number 20 says, work output of turbine is less than the work input to the pump. Sorry, I will read it again. Work output of turbine is, there should be some blank space. Okay. And we have to tell whether it is less or more or equal to. Okay. So if the turbine work output is less than the pump work, then what will happen? We are getting net negative work output. Okay. Our system is consuming more work than it is producing. Okay. So it is just a useless, useless cycle, useless power plant. In an actual power plant, the turbine output should be very, very large as compared to your pump work input. Okay. The work output turbine should be much larger as compared to work input to the pump. Okay. Then only you will get some significant amount of net work output. Okay. So this was question number 20. We will move question number 21. Question number 21 says, an isentropic steam turbine receives 2 kilogram per second of steam at 6 megapascal and 500 degrees Celsius and leaps at a pressure of 0.3 megapascal. If the expansion process can be assumed to be isentropic, then we have to tell the work output from the turbine. Okay. At inlet, turbine receives 2 kilogram per second of steam at 6 megapascal, 500 degrees Celsius and leaps at 0.3 megapascal. If the expansion process can be assumed to be isentropic means constant entropy process, then we have to find the work output. So work output will be equal to enthalpy at inlet minus enthalpy at outlet. Okay, but to find these enthalpy values, we can use the steam table. At inlet, two things are given: pressure and temperature. So we can find enthalpy using steam table, but at outlet only pressure is given. So we need one more, variable. So what will be that one more variable? That will be entropy. Okay, because it is given that we can assume this process to be isentropic. So entropy at inlet will be entropy at outlet. Okay, and we will have to multiply this thing with mass flow rate. Okay, so we can find this as entropy at inlet using steam table. Okay, so I will open some steam table and we'll find out this value. We'll have to use superheated, table. These tables are given in the appendix of any, standard thermodynamics textbook, or steam tables also comes separately. Okay, so superheated water at 500 degrees Celsius, we'll have to check. 500 degrees Celsius, but the pressure is 6 ampere. So we will scroll down to check it at 6 ampere. Okay, so here it is 6 ampere, 6 megapascal and 500 degrees Celsius. What we have to find? We have to check S. S is given so S is given here 6.8826 kilojoule kg Kelvin, and H is given 3423.1 kilojoule per kg. Okay, this is at inlet. Now we have to find this H at outlet. So at outlet, what is given? pressure is given 0.3 megapascal. So we will have to check the superheated or maybe saturated table for 0.3 ampere. Okay, this is saturated table. 0.3 ampere. 0.3 ampere means 300 kilopascal. So 300 kilopascal is here. So at this value, we can check entropy where it is. Here it is. At at 0.3 ampere or 300 kilopascal, enthalpy of liquid, saturated liquid is 1.616717 kilojoule per kg Kelvin. Enthalpy of saturated gas is 6.9917 kilojoule per kg Kelvin, and this difference SF, Sg minus Sf, this is 0.53200 kilojoule per Kelvin. Okay. And S at this point is what? S of outlet will be equal to S of inlet, and S at inlet we have found to be 6.8826. Okay, so this S will be equal to what? SF plus X into SFG. Okay, S is the quality, X is the quality. Okay, so if you put these values, then you will find that 6.8826 is equal to 1.6717 plus X into 5.3200. And if you solve this equation, you can find X. You will find the quality. Okay. So if you calculate this value, it will come out to be 0.9794. I have already calculated this value. You can calculate it by yourself. Okay. So it is 97.94%. This is the quality. Okay. So now we can find the enthalpy at outlet. Okay. Enthalpy at outlet will be what? It will be HF plus X into HFG. Okay. So these values again you can find from the table. Okay. What are these values in the table? HF. Where is HF? This is HF in the table. So 561.43 plus 0.9794 into 2163.5 2163.5 kilojoule per kg. Okay, so you can calculate this value. And I have calculated this, and it is coming out to be around 2675 kilojoule per kg. Okay. So now you can calculate what you can calculate work output. Okay. Work output. This will be equal to H of inlet minus H of outlet. Okay. So at inlet, this value was 33423.1. At outlet is 2675 kilojoule per kg. Okay. So you can calculate this thing, and it will come out to be it is coming 748.1 kilojoule per kg. And we have to find total work output. Okay. So work output will be equal to mass flow rate of steam multiplied by this value 748.1 kilojoule per kg. So what is mass flow rate of steam? It is 2 kilogram per second. Okay. Just multiply by this thing by 2. So you will get 1496.2 kilojoule. Okay. Per second. Okay. Joule per second is basically watt. So 1496.2 kilowatt, or in megawatt terms, you can write it as 1.49 megawatt. Okay. So this will be our work output. Okay. I hope this is clear, and we can move to the next question. To solve any numerical, you should be, familiar with the steam table, how to use them, or, look up for the values. Okay. In any exam, either you will be provided steam tables or values directly can also be given. Okay. So question number 22, this is also a numerical question. It says that consider a steam power plant, okay, operating on a simple ideal Rankine cycle. Fine. Steam enters turbine at 3 megapascal. Okay. What was the value here? No, it was different. Anyway, steam enters turbine at 3 megapascal and 350 degrees Celsius and is condensed in the condenser at a pressure of 75 kilopascal. We have to find the thermal efficiency of this cycle. Okay. First, let us make the TS diagram. When you make the TS diagram, it becomes easy that what are the properties given and what properties you need to find out from the table. This is the ideal Rankine cycle. Okay. Now what is given? A steam power plant operating at simple steam enters the turbine at 3 megapascal. So turbine is from 3 to 4, right? This is our turbine. So inlet of turbine means this point number 3. Okay. So pressure at point 3, it is given. P3 is given as how much? 3 megapascal. And temperature is also given. T3 is equal to 350 degrees Celsius. Fine. And is condensed in the condenser at a pressure of 75 kilopascal. So at point 3, two quantities are given, but at point point 4, only one quantity is given. But to fix the state, we need two, variables. So what should be the another variable? Another variable should be entropy. As we did in the previous question, we assume that expansion, not assumed, actually it was given in the question that expansion process in the turbine is isentropic, and here also it is ideal Rankine cycle. So the process, all the processes are ideal, and ideal expansion process means isentropic process. Okay, so at point 3 we can find the entropy from the steam tables, and so from steam table we can find the entropy from the steam table at point 3. So we will have two quantities, two variables at point 4 as well, entropy and this pressure. Okay, so first let us find other quantities at point 3. So where is that book? Okay, 3 megapascal and 350 degrees Celsius. So here it is, 3 megapascal. Sorry, it is so saturated. We need to check superheated. Okay, this is 3 megapascal and temperature is 350 degrees Celsius. 350 degrees Celsius. So these are the values which we need. Just zoom this thing. What is given? Specific volume is given as 0. Just give me a second. Okay, so specific volume is given 0.09056 meter cube per kg. Okay, what else is given? Enthalpy is given. How much it is? 3116.1 kilojoule per kg. Okay, and entropy is given 6.7450 kilojoule per kg Kelvin. Okay, so these are the quantities given at point 3. So now we need to find the values at point, point 4, outlet of turbine. So what is given at point 4? P4 is given. How much it is? It is given 75 kilopascal. So it is 75 kilopascal. Entropy will be equal to entropy at inlet of turbine, S3. Okay, so S4 will be equal to S3. That is given 6.7450 kilojoule per kg Kelvin. Okay, so from saturation table, we can find the quality now. Okay, where's saturation table? So this is superheated table. This is saturated table. We have to check at 75. Okay, so these are the values. Okay, we will check the entropy values, and entropy as S4 will be equal to SF at 0.4 plus X into X is quality. Okay, SFG at 4. Okay, so we can substitute all these values and values from steam table. So S4 we have found out to be 6.7450 equal to SF is given in table. It is 1.2132 plus X into it is given 6.2426. Okay, so from this equation we can find value of X. Okay, so value of X, if you solve this, it will come out to be 0.8861. Okay, you can check the calculation. So this is the quality at 0.4. So now we have quality. So now we can find enthalpy at H4. So enthalpy at H4 will be equal to HF at 0.4 plus quality into HFG at 0.4. Okay, so again these values we will find from table. So what are these values? Enthalpy values. So HF is 384.44. All these values are in kilojoule per kg. Okay, plus 0.8861 into HFG, and HFG is given 2278. Okay, all these values will be in kilojoule per kg. And if we calculate this value, then it comes out to be 2403 kilojoule per kg. You can please check these calculations. I hope it is correct. Okay, so we have found the values at 0.3 and 0.4. Okay, what else we need? What we have to find? We have to find the thermal efficiency. Okay, to calculate the thermal efficiency, what we need? We need net work output and net heat input. Okay, what we need? Thermal efficiency. We need net work output and net heat input. And for net work input, we need work output from turbine minus work input to the pump. Okay. For turbine, we can calculate work output from H3 minus H4. And for pump, it will be what? It will be H2 minus H1. Okay. Okay. So for this Wn, we need enthalpy values at 0.1 and 0.2. Okay. So we will again find this from the steam table. Okay. What else we need? We need Qin. So Qin will be equal to H3 minus H2. So again, we need enthalpy values at 0.3 and 0.2. Okay. So these are the values we need. Okay. H4 we have already found out. Okay. H4 we have already found out. H3 we have found out from the table. Now we need to find these, four values, H1, H3, and H2. Okay. So how will we find? Point one, pump input. It is given simple, Rankine cycle. So at point one, pump input, pump inlet, water will be in saturated liquid state. Okay. So we will check saturated water tables. And what is given, what we have is pressure. Okay. Pressure at 0.4 and 0.1, it will be equal. Okay. P1 will be equal to P4 because condensation process is isobaric process. So P4 we have, it is given in question to be 75 kilopascal. Okay. So from saturated table, we can find H1. H1 means enthalpy of saturated liquid. So the same value, enthalpy of saturated liquid, it is how much? Okay. So in the table, it is given H1, that is enthalpy of saturated liquid at 75 kilopascal. It is given to be 384.44. Okay. So here it is given kilojoule per kg. And what else? Specific volume. Where is specific volume we need? Here specific volume. It is given to be 0.001037 meter cube per kg. Okay. So we have all these values at 0.1 as well. Oh, sorry, I have made a mistake here. Pump work is not H2 minus H1. Okay. Pump work we can find using volume, specific volume multiplied by pressure rise. Okay. So P1 we have, H1 we have, and V1 we have. Okay. So now what else we need? Now we need values at 0.2, outlet of pump. Outlet of pump means inlet of boiler. Okay. So what is given in the question about outlet of pump? Nothing is given. Okay, no problem. At 0.2, we know that pressure at point 2 and pressure at point 3, they will be equal because the heat addition process in boiler is isobaric. Okay. So P2 will be equal to P3, and P3 is given to be, it is given 3 megapascal. Okay, 3 megapascal. And since it is an ideal cycle, so entropy at point 2 will be equal to entropy at point 1. Okay. So we will use supercooled liquid table. Not supercooled liquid, actually it is called compressed liquid. Okay. So what we have? We have pressure 3 megapascal. Okay. Sorry, we don't need this value. Okay. Why? Because the pump work we have already discussed that it is given by a specific volume minus a specific volume into pressure rise. Okay. So P2 we have, P1 we have, V already we have, then there is no need to find any other, quantity. So we can find other quantities, but they will be of no use. Okay. These values are enough to calculate pump work. Okay. So just substitute these values. V1 we have found, it is 0.001037 meter cube per, I will make it little smaller, 0.001037 meter cube per kg multiplied by P2. P2 is 3 megapascal. So in kilopascal, you can write 3000 minus P1. P1, how much P1? It is 75. 75 kilopascal. Both values are in kilopascal. Okay. So if you calculate this thing, so it will come out to be 3.03 kilojoule per kg. Okay. So pump work we have found out. And work output from turbine, that is H4 minus H3. Have we already calculated that or not? Okay. So H3 we had found from table, and its value was 3116. 3116.1 minus H4 is, H4 we have found out to be 2403. 2403. Okay, kilojoule per kg. And if you subtract this, then it will come out to be 713.1 kilojoule per kg. Please check these values and calculation. Okay, so this is the turbine work. So the net work output will be what? turbine work output minus pump work input. Okay. So 713.1 minus pump work input was 3.03 kilojoule per kg. Okay. So the net work output will be 710.1 kilojoule per kg. Okay. This is our net work output. Okay. And heat input Q in. This is what? H3 minus H2. H3, do we have H3? Yes, H3 we have. It is 3116.1. 3116.1 minus H2 we have. We had calculated H2, where it is. Okay, H2 we have not calculated. Let us first calculate H2. Okay, so H2 is basically enthalpy at pump outlet. Okay, so that will be equal to enthalpy at pump inlet plus work input of pump. Okay, right? Just energy conservation. Okay, so H1 we had already found out, and it was how much? 384.44 plus 3.03 kilojoule per kg. Just check these values. H1 and pump work is 0.03. Okay. So H2 we will find out that this is equal to 387.47 kilojoule per kg. Okay, so now you have H2. Okay, so just substitute this H2 to calculate Qn. So it will be equal to H3 minus H2, and H3H. Where is H3? H3 is 3116.1. 6.1. 3116.1 minus 387.47 kilojoule per kg. Okay, so if you calculate this value, so it will come out to be 2728.6 kilojoule per kg. Okay, so now we have everything. Okay, we have net work output, we have Q in. So now we can calculate efficiency. So that will be equal to net work output divided by total energy input. Okay, so what is net work output? 710 divided by 2728.6 kilojoule per kg. Okay, So how much it is coming? It is coming 0.26, okay, or 26%. Okay. So you can see it is, very less. And in the question, it was given that it is ideal cycle, but in real, there will be irreversibilities involved. So this efficiency will be even less. It will be less than 26%. Okay. So efficiencies are very less. So what we need to improve the efficiency. To improve the efficiency, we have discussed that there are few underlying concepts. One is we should try to have a cycle that is even more close to ideal one. Okay, more close to ideal cycle. Okay, because ideal cycles have the maximum efficiency. So if you are closer to ideal one, then you will get the better efficiency. And maximize the average temperature of heat addition and minimize the average temperature of heat rejection. Okay, so these are the requirement to increase the efficiency. Okay, so in next few weeks, you will study what are the modifications that we make to the Rankine cycle, and the modified Rankine cycle will produce more efficiency as compared to simple one. Okay, so whatever you are doing, the main purpose of that is that we want to maximize the average temperature of heat addition, and we want to minimize the average temperature of heat rejection. Okay, so that is how we increase the efficiency. So there are a lot of ways. Okay, we are reheating, there are regeneration. Okay, so a lot of modifications are there. And also, as we discussed in some previous question, that there was something called economizer. So what it does is that in the boiler, how you are getting heat input, you are burning something, burning some fuel. Okay, so those burned gases, the exhaust gases, the residual gases, they are quite hot. And if you, instead of simply throwing out those gases into environment, we can use the heat content of those gases to heat the water. Okay, so this is one of the way to utilize of waste heat. Okay, so I hope all these questions are clear. For the numerical, the most important thing is that you should have the values at all the points, especially the enthalpy values. Okay, so to calculate the enthalpy values, to find any values, you need at least uh, two variables to determine the system, to determine the state of the system. Okay, so sometimes it is given in the question, and sometimes you need to find it by yourself. Okay, sometimes the process are isentropic. So at one end the entropy is given, so the same entropy will be at the another end. So using these types of concepts, you can find all the values at all the points. So for calculating efficiency or some work output or input, we need to have enthalpy values. Okay, so better to find all those values first, then proceed. Okay, so this was the last question. Okay, so we'll stop here. Thank you.